Good afternoon. Today I will present our work on enabling software updates of integrity-enforced operating systems. Integrity enforcement is a mechanism that ensures that the operating system executes expected software in the expected configuration. Monitoring systems verify the integrity of operating systems by leveraging trusted computing techniques. Unfortunately, software updates change operating systems' integrity, causing monitoring systems to report integrity violations, and that makes the monitoring impractical. Software consists of files such as executables, configuration files, and dynamic libraries. Each file's integrity is represented by the cryptographic hash calculated over file's content. Trusted computing techniques allow measuring, enforcing, and reporting the software integrity. For example, when the kernel loads a file, it calculates the cryptographic hash over that file to verify its integrity. Files tampered by an adversary are detected because the hashes differ from the expected values. Unfortunately, we also observe integrity violations after updating the software, and that's because new hashes do not match the expected ones. In the rest of this talk, we will walk through a system design that enables software updates of integrity-enforced operating systems. Every software update is first published to the software repository, and from there it's distributed to operating systems. A package manager is a software running inside the operating system that downloads software updates from the repository and installs them by extracting newer versions of executables, configuration files, and dynamic libraries from the package to the file system. The integrity of updated files is measured and stored in a tamper-proof fashion. Monitoring systems learn what software has been loaded on a remote computer, but they report integrity violations after the operating system gets updated. To mitigate this, we propose a Trusted Software Repository, TSR in short. This is a proxy between the operating system and software repositories. TSR implements a sanitization mechanism that modifies software packages in a way software updates are verifiable by the monitoring system. TSR has its own signing keys to certify that the package was sanitized. These keys are protected with the Intel SGX. Furthermore, TSR tolerates malicious mirrors that might be used by an adversary to compromise the operating system. Specifically, an adversary can launch the replay attack to serve outdated packages containing known vulnerabilities, as well as she can perform the freeze attack to hide software updates from the operating system. TSR tolerates malicious mirrors by obtaining a quorum from a list of defined mirrors. Our assumption here is that the majority of mirrors is trustworthy. The sanitization mechanism consists of modifying each software package available in the repository to make it be safely installed in the integrity-enforced operating system. Let's see how the TSR modifies software packages. A software package is composed of three parts. The first one, package header, contains a digital signature certifying authenticity and integrity of the package. Second part, control, contains meta information and installation scripts. Finally, the last part, package contents, consists of software-specific files. These are binaries, configuration files, and so on. We are interested in the software-specific files because during the package installation, they are extracted to the file system, causing integrity violations. The sanitization process adds digital signatures for each file, allowing monitoring systems to verify that the file is legitimate. Installation scripts also cause integrity violation because they change systems configuration. To design proper sanitization technique, we performed an analysis of real-world software packages available in Alpine Linux repositories to learn what exactly these scripts do. We found out that about 97% of packages do not contain any script, while 81% of the remaining packages contain scripts that alter the operating system configuration. We analyzed what kind of commands these scripts execute. We found that the majority of scripts just modify users and groups in the operating system. User and group management changes free configuration files in a well-defined way. However, the exact file's contents depend on the order in which users and groups are created. To make this process deterministic, the sanitization process first scans all scripts in all packages, then extracts from these scripts all users and groups creation commands, then predicts how the configuration files would look like after executing all these commands. Then it issues digital signatures of the predicted configuration and files located inside the package. Finally, it modifies all scripts in all files so they execute all commands in the same order. Thanks to the sanitization, 99.76% of all packages can be safely installed without violating the operating system integrity. We performed a series of experiments to evaluate the sanitization process, the mechanism of tolerating compromise mirrors, as well as impact of Intel SGX on our prototype implementation of TSR. In one of the experiments, we answered the question, how much time does it take to sanitize a single package? We were interested in how does the sanitization time changes with the number of files inside the package and with the change of the uncompressed package size. We observed that the signature generation and package extraction become dominant factors of the sanitization time, causing higher sanitization times for packages with larger number of files or larger package sizes. The sanitization time is not evenly distributed. It changes from 11 milliseconds in the 50th percentile to up to 30 seconds in the 100th percentile. We observed the highest sanitization times for packages which sizes exceeded the available EPC memory. The total sanitization time of all pre-downloaded packages takes 13 minutes. It's practical because in practice, after the repository is initialized, only a subset of packages needs to be updated, sanitized between new updates release. That occurs at least at hourly or daily intervals. We launched another experiment to answer the question, what is the overhead of tolerating compromise mirrors? In this experiment, TSR deployed in Europe communicates with Alpine mirrors located in different geographical locations. We were interested in the latency of downloading a repository index from the TSR. Please note that to download the repository index, TSR had first to download the repository index from the defined mirrors, get a quorum, repackage the index, and only then return it to the requester running on a different machine located inside the same data center. In this experiment, we were increasing the number of mirrors used by TSR to establish a quorum. Depending on the number of mirrors available on the same continent, TSR required from 400 milliseconds up to 1 second to return the repository index. The latencies were much higher when TSR used only mirrors located on different continents because of higher network latencies. In scenarios where TSR used mirrors located on all continents, the higher network latencies to mirrors located in other continents did not dominate the index download latency. This is a result of the TSR implementation that stores information about the latency to individual mirrors, and for subsequent requests, TSR first contacts mirrors with lower latencies. TSR required up to 2 seconds to establish a quorum from official Alpine mirrors distributed over 3 continents. In summary, TSR enables software updates for integrity-enforced operating systems. It implements the sanitization process that digitally signs files inside the package and modifies installation scripts. And finally, TSR tolerates a minority of mirrors exhibiting Byzantine behavior. Thank you, and I'm happy now to answer your questions.